asked to share our project on 3D geodata modeling and the management system for Singapore and its applications. And this is a very time-consuming project. It is carried out jointly with BCA, LTA, and the URA. So Kiefer Cham is the driver behind this project. Of course, we have our team members. So the major player is Dr. Pan. Also, Peng Pai is one of our collaborators. He's with us. This project is a direct response to the call for challenges, also called L2 NSC. The one of the challenges is how to reduce the construction cost by 50%. So if we want to cut the construction cost by 50%, it simply means they are fat in the design or construction. So in other words, there are a lot of uncertainties in the geology as well as in the rock and soil properties. Based on the report from the ICE London, so they experience the same problem. So about 50% of the cost of project delays are related to unforeseen ground conditions. So now the task is how to reduce the uncertainties in the ground model or in geology. So I'm going to briefly introduce and how the 3D geological model is constructed. Then after that, I'm going to share with you the so-called web-based geodata modeling and management system. So basically, you can use your own computer to access this system. Then after that, I'm going to give two simple examples to illustrate the application of this system. We do have a 2D geological map showing over here. Basically, it tells you the geological distributions for the island. And recently, there's also a bedrock geological model constructed by BCA and by collaborating with British Geological Survey. And so this deals mainly with hard rocks. So we have a surface model, we have hard rock, but we don't have something in between. In fact, more than 90% of our constructions is within the soil, the so-called subsoil. So that's why we need a subsoil model. The subsoil model is constructed by making use of the geological borehole data, which BC has been collecting over the years. So altogether, we have more than 60,000 borehole data. And together with the geotechnical testing data, and in fact, in the same database, there are also geotechnical testing data, for example, SPD and in situ testing, as well as some laboratory testing data. We need to make use of the 2D geological map, which you have just seen, and combined with DEM, which is the elevation. So by putting them together, we can construct the 3D geological model. But however, before we do this, we really have to validate the data because some of the data may not be consistent. Okay, so number one problem is the elevation. So the borehole may have been taken 20 years ago, but now even the elevation may have been changed. And of course, there are mistakes here and there. There are inconsistencies in the data. So all those has to be validated. And then we also have a team to evaluate uncertainties in the model, because your model can only be as good as the availability of the data. So if you don't have many data, or if the boreholes are far apart, so the uncertainties of the model will not be very high. So we need to inform the users okay, how accurate is a model, at least for a particular zone. Then after that, we have a 3D and geological model. And once we have the model, we can put it online and together with other database. For example, you can see the borehole if the borehole is available. Okay, I believe now you can see the borehole and using the URA website, but you can also see the borehole data using our system. But in addition to the borehole data, we will also be able to share other information with you. And using the online system, you will also be able to see, for example, the 3D geological model, and as well as the cross sections. Okay, so if you later I'm going to explain if you draw a line on a Google map, so we will be able to show you a cross section along that line. So that will lead to the web-based geodata management system. So in other words, if you are given a password and if you can have access to this system, and so you will be able to make use of the model as well as the information provided by this system. So at the moment, we are working together with URA and LTA on some of the projects to validate the model as well as fine-tune the models. So here are the data distribution, I should say the borehole data distribution along the whole island. As you can see in the natural reserve, and we don't have many data. So in other words, the model over here will be very inaccurate. So the blue points are mainly from HDB, and so some of the boreholes are very shallow. So in other words, you will not be able to have too much information related to rock and related to the hard layers, and the green ones are from LTA, and the rest are from other agencies as well as developers. So what we do is we establish grid lines. We try to build the fence diagrams along those grid lines first, and then by putting together the grid lines, we can have our model. And also we subdivide the whole island into 9 zones, and the reason for that is because we only have a limited amount of software as well as manpower, so we have to do it in batches. We are using the software called the subsurface view, and occasionally we also use GoCat, but most of the time we're using subsurface view. So the procedure for the 3D geological modeling. So step number 1 is we construct cross sections. So basically, we use the borehole data. We use our geologists to do interpretation for the geological formations in between the boreholes. So from there, we have a cross section. So once we have a sufficient cross section, we put them together. We have a so-called fence diagram. So once we have the fence diagram, we use a software to do interpretation and to interpolate the models in between. Then we have the so-called 3D geological model. Okay, so this is for zone 3. Basically covers the Topayo and Almorque. So we choose this area because every time we have a project meeting, which will be at the BC Academy, so it's located somewhere over here. So once you have the model, we also have to refine the model, as I've said. The models contain a lot of uncertainties. So the first step is we have to assess the uncertainties, and sometimes in the boundary of the key geological formations. So for example, I mean, at this location, it could be the boundary between Jurong Formation and the Bukit Timah Formation. That's actually a fault somewhere around here. So if you want to have a more precise information along this boundary, because it is a boundary which is more difficult to interpret, so you will need some additional geological data. But another way to estimate uncertainties is to use geostatistical method or use artificial intelligence. So I said this before, we can refine the 3D geological model by using additional borehole data or available geological information. So from there, we can have additional fence diagram, and we will be able to refine the accuracy of the model. For a real application, we can make use of the new borehole data, which will be taken for that particular project, as well as other geological information or geophysical data. And by combining with those actual data, we will be able to refine the model. So I'm going to give an example for this application. So here is just one example to show you the differences between the refinement and before the refinement. So this is the fence diagram. In fact, this fence diagram is for this red particular location. Okay, so for the so-called zone 2, which is related to this mount fibers, which is not far from us. So as I've said, so one set you have a Jurong formation, another set you can have Bukit Timah formation. So at the boundary, which can be more complicated. So to have a better interpretation, you will need some actual information, actual data. So if we can have some additional fence diagrams constructed as showing over here, and then the cross-section can be much different, as you can see from here. So this is the cross-section from here for the old model, and this is the cross-section after some additional fence diagrams has been added in. So basically, it just shows your model can only be as reliable as the availability of the data. So the model by no means is going to replace your future set investigation work. You still have to do your set investigation, and the model here will only provide you with more informed information, and for you to do a better set investigation work. I'm going to explain this at a later stage. I also like to say a few words on how we estimate the uncertainties. So one way is to compare with the real borehole data. So we can get additional borehole data from the recent projects. From there, we will be able to compare, for example, the raw head. The raw head basically is the weathering grade 3 below and above. So from here, we will be able to see whether our model, in terms of the interface, is reliable, but compare our model with the real borehole data. Another way, of course, is to do some statistical analysis using mathematics to have an estimation of the uncertainties involved. Now let's come to the 3D web-based geodata modeling and management system. So if you log into our web page, so on one side you have your 2D map, on the other side you have your 3D geological model. Within the same system, you will also be able to see some of the big models if you have. Okay, for example, the Marina Bay Sands and etc. etc. So this is one of the examples. So you will be able to combine your beam and together with the geological formations. And in fact, we will also be able to show the faults. So that will be the hard rock model and developed by BC and together with BGS. So that part of information can also be shown within the same system. Using the same system, if you can input coordinates, so if there's a real borehole data, and the real borehole information can be assessed. So if there's no real borehole data, synthetic borehole data will be generated. So this is one of the examples. So in other words, you can generate so-called virtual borehole anywhere you like, just by draw a point on the map or just enter the coordinates or anywhere you like. Or you can draw a line. It doesn't have to be a straight line. It can be a curve. Okay. and then we will give you the cross-section along the straight line. So this cross-section is generated using the 3D geological model. If you draw a circle, it could be a square and could be any other shape. So we will be able to give you the 3D geological model for that particular location or that particular site. So this is what you can do with the model. Now let's move on to two case histories. And the case number one is detection of ancient river. So I'm a geotechnical engineer, so sometimes I have to deal with design and construction. So we all know wherever there's a soft soil, so we need to pay more attention. But how do you know there's a soft soil? So your geological model will be able to help. So sometimes we see the soft soil is concentrated at one location. So this sometimes could be related to the ancient rivers in the past. Of course, if you know there is a river now, okay, you know the soil below the river and could be soft. But the problem is if there isn't a river, and how do you associate the soft clay and with the past geological history? So one example is the Ritual River, which is located over here. So this is an enlarged view of the river. So currently the river flows from here to here. So of course along the river, if you encounter soft soils, which is reasonable. But the problem is even the surrounding areas which are apart from the river, for example, over here, you also have the soft deposits. Okay, so those soft deposits are related actually to the ancient river, okay, in the past. So if you use our geological model, so you will be able to construct the 3D model over here, and you will be able to peel them off layer by layer. So from there, you will be able to see the column formation, which covers not just along the path of the current river, but also on the other side of the river. So this is actually the ancient Ritual River in the past. So once you know the distribution over here, and so you will have additional information and for your site investigation. So if you have a borehole over here, so you can anticipate, I mean, even the area before and after the borehole, you are going to get soft clay. So the information will be useful for geotechnical design as well as for planning. Another example is what we are working together now with LTA. So there is a possibility a MRT line could be constructed somewhere along Bishan Park. So if this is a schematic alignment, so the first thing LT would like to know, even during the planning stage, is what are the ground conditions, what are the geology at this particular site. So assuming we have not done any site investigation work, we don't have any borehole, we can always go to the 3D geological model and go to our database and to see whether we have existing boreholes. So we do have. So we do have boreholes from previous projects, but mainly from HDB projects, because there's a lot of HDB blocks surrounding Bishan Park. So the blue is for the borehole depths greater than 25 meters, and the red are the borehole depths less than 25 meters. Unfortunately, there isn't any borehole along the MRT line, or at least the proposed MRT line. So then how are we going to, let's see, construct the cross-section? But if we are using the 3D geological model, this is possible. So using the existing borehole data, we can have our fence diagrams, you can have our 3D geological model. And using this model, and we actually can see there are soft deposits, okay, as showing over here. And this is actually associated with a river. And there's a small creek physically you can see if you have been to Bishan Park. Okay, so the river is somewhere over here, which is not far from the alignment of the MRT. So of course below this you have your Bukit Timah granite given in red. Even though within the Bukit Timah granite you want to know what's the weathering depths. Okay, and so from there you will have informed information on where, how deep your tunnel should be or your station should be. Let's say if we don't have any new borehole data yet, and just make use of the model, and we could be able to construct the cross-section along the MRT alignment as shown over here. So basically, the accuracy is somewhere between 5 to 10 meters. So in other words, in terms of the rock head or the soil rock interface, so this line can have an error of somewhere between 5 to 15 meters. So this may not be good enough for a tunneling construction company. Then subsequently, we were given some borehole data and taken by LTA, but unfortunately, there's only 8 boreholes along this line, along this alignment. So if we make use of the 8 borehole, of course, we can construct a cross-section. So that cross-section will look like this. So if you compare this cross-section and the cross-section which we constructed using the borehole only, using the model only, we are, in other words, and we don't have any new borehole data yet, and you can see the differences. So between the two, I would say our 3D geological model is more realistic than the cross-section given by the 8 boreholes. So that indicates the usefulness of this 3D geological model. But however, if you combine all the data, so just now we only have 8 points along the MRT line, but however, for this sand investigation, there are altogether 33 boreholes. Okay, if you make use of the 33 boreholes, you combine the 33 boreholes with the existing data, and you will be able to refine your model. So once you have your model refined, then you will be able to have a new cross-section. So this is a cross-section. This cross-section is created by combining the 25 new boreholes with the 3D geological model. In other words, the model updated by the 25 new boreholes. We only use 25 because we want to keep the other 8 boreholes for verification. Okay, and then you can see the cross sections. So now the new cross sections has been improved as compared to just the pure model. This cross section is certainly much better than the cross section given by the 8 boreholes only. Okay, if you combine the extra 8 boreholes, in other words, if you use 33 new boreholes, you can see the uncertainties can be much reduced from somewhere between 3 to 8 to 1 to 4. And this 3 to 8, 1 to 4 is a pure comparison between the real borehole data and the rock head, which is generated by the model. Okay. If you have some additional borehole data, let's say you don't have many, if you add in so another maybe 10 or less than a dozen. So the model can be further improved with accuracy somewhere between 1 to 2 meters. So I believe this is accurate enough for LTE's purpose. So from here, even before you start your project, at least you can have some informed information. For example, where you should sink your boreholes. You have to have more boreholes somewhere which is a soft deposits are encountered, and also you can you know how many boreholes are sufficient to give you a realistic cross section for your MRT construction. So with this, I conclude my presentation. So as a summary, so basically the 3D geological model and the web sharing system have been established. So the system will be able to provide and the borehole and other geological information. We'll be able to draw virtual cross-section online. We'll be able to build. And at the moment, we cannot update yet. Okay, but the target is to updating in the near future of the 3D geological model for a given area, as well as construction site. Okay, as far as the updating for a given area. So once you have your additional borehole data, and that can be updated. But for the overall model, okay, so we will not be able to let you to update the model at the moment. I have given two examples to illustrate the application, and the first one is detection of ancient river, and the second one is the tunneling project at Bishan Park. I actually have one more example for Pongo North, but I don't think we have time to cover that. So that explains the typo here. I should have changed the 3 into 2. Finally, I'd like to acknowledge the funding support from the Ministry of National Development, as well as the National Research Foundation for the general support for this program. Yeah, thank you very much.